Welcome to qnawire.
Given the system, the problem asks us what is the maximum force that the man can exert on the rope such that the board underneath him will not move on the floor. We can solve this problem by applying Newton's law of motion. First, we need to draw the individual forces acting on each masses. Let's start first with the man. Assuming this is the man, simple model of the man, the forces acting on its body are its weight, the normal force, and the tension of the rope on this direction. Applying Newton's law of motion, since what we are achieving is a body in equilibrium or not moving or at rest, we can apply the first law of motion that states that the summation of the forces is equals to 0. Vertically, the forces on this plane are the normal force, which is the same direction as the tension, and the weight, which is negative since opposite the direction of the two. Or simply, this is equal to 0. Simplifying and isolating the normal force to the left side equation, we have n sub big M is equal to big M times G, which is the weight of the man, minus the tension. Now, for the board, denoted as small m, assuming this is the board, the forces acting on its body are its weight, the normal force, the tension of the rope, and a friction opposite its supposed movement, and since it is underneath the man, it also experiences a normal force from the man. So the summation of this force, of these forces are normal force, negative of the normal force of the man in its opposite direction, negative of the weight of the board, and that's all. We know that the summation is equals to 0. Then the equation becomes isolating the normal force of the board to the left side equation, then equation becomes now for the horizontal plane, the summation of the forces are the tension and the negative of the friction force. This is negative since opposite the tension on the rope. And the summation is also equal to 0, since what we are achieving is equilibrium. So the equation becomes, we know that friction is equals to the product of the coefficient and the normal force. Then T is equals to mu n sub small m. And from the equation we have earlier for the normal force of the board, then these equations become n the normal force of the man plus the weight of the board. Now, using this equation, let's note this as equation 1. Let's insert it to this equation. Let's denote this as equation 2. Then, equation 2 becomes T is equals to mu multiplied by this quantity. Expanding, we have rearranging and regrouping, then simplifying, since the tension is the force that what we are looking for. Let's isolate it to the left side equation. The equation becomes T is equals to this quantity.